Welcome to Chapter 5, Section 5, the Substitution Rule. In this video, I'm using slides provided for Stewart's Calculus Early Transcendentals 8th edition, and I'm going to walk through Stewart's slides, making some comments, adding in some additional work where he has worked out some solutions to some example problems, and then at the end of the video, I will toggle over and work through some homework problems that I'm assigning to my own students. So the first few slides in here, the first 6, are talking specifically about the substitution rule, and it's building on the fundamental theorem, and it definitely is sort of a demonstration of the reverse chain rule. So what we're seeing here in number 1 right at the top of this screen is an integral of 2x times the square root of 1 plus x squared with respect to x. And on the next slide, we're going to be making some substitution. So we'll see the substitution rule in motion for the first time. And what's happening here, so notice that the original problem or question has been rewritten here. And the thing that you're going to be looking for in order to use the substitution rule is this. We see a square root function here, but inside the square root function, I'm seeing another function, the 1 plus x squared function. So already that's like f of g of x, right? Nested functions. The interesting thing is that the inner function, 1 plus x squared, if you were to take the derivative of it, in this particular case, you get 2x, which are the other factors that are outside of that statement f of g of x. So what we want to do in the substitution rule is to take the inner function and call it u. So that's often referred to as a let statement. So we will let u equal 1 plus x squared. And the author doesn't write this out explicitly. Oh, it's up here actually. So at the top of your top right corner of your screen, u is being let equal to 1 plus x squared. And if you take the derivative of both sides of that equation with, not really with respect to x. On the right hand side, we're seeing with respect to x. On the left hand side, it's really with respect to u. So we're taking the derivative of both sides, and we get this statement right here. And what's not shown in this particular instance is a step that we will see later. Sometimes this original derivative of the u function does have to be modified a little bit. So we'll see that again in a later problem. Now the substitution is made, so we see that this inner function, 1 plus x squared, moving to the right, 1 plus x squared, there it is. The 2x dx has been placed at the end of the statement now. Originally, the 2x was in front and the dx was at the end, but now we see that both of them are being placed after the square root symbol. And then the substitution is made. We see the square root of u, and then at the end, the 2x dx has been replaced with du. And remember that that is allowed to happen because du equals 2x dx. So it's really a double substitution. In this case, the function underneath the square root symbol is being replaced with a u, and all the rest of the factors are being replaced with du. Now we can do this integration, and if I were doing this, no, let's stay with red maybe. The next thing I would do if I were showing all of my work is I would rewrite this one more time as u to the 1/2 power du, so that when I integrate, I can increase the exponent by 1, making it 3 halves, divide by the new exponent of 3 halves, which is the same thing as multiplying by its reciprocal, 2/3. So that takes us to this expression. Don't forget to put plus c, that is your unknown constant value. And then, now that the integration is done, or we found the antiderivative, in terms of u, we need to back substitute, replacing the value of u with 1 plus x squared. Don't forget your plus c, and you've got yourself a final answer. Not bad, and you might want to rewatch that one more time just to see it play out. And the same rule, I suppose we could say, applies here when we're working with the substitution rule. You could take your final answer of 2/3 1 plus x squared to the 3 halves plus c. You could take the derivative of it with respect to x, multiplying the exponent times the leading coefficient. Those are going to cancel each other out. Decreasing the exponent by 1 changes it from 3 halves down to 1 half. And don't forget to apply the chain rule. This inner function, which I'm highlighting in green, the 1 plus x squared, we do have to multiply by the derivative of that inner function by the chain rule, and we see that appearing out here. And after the two fractions cancel each other out, and we convert this expression back into an actual square root function, these are the components that we're left with. And you see all of those appearing here. Again, the 1/2 power being converted back to a square root, and the 2x is written in front instead of at the end. But it's all multiplication, so all the components are there. It doesn't matter the order that we write them. And if you look at the top of your screen, right up here, you can see that that is equivalent to the derivative that we just took at the bottom right-hand corner of your screen. So it works. We can double check and see if we integrated correctly by taking the derivative again and seeing if we get the original expression that we were integrating. When am I allowed to use this method? You're allowed to use this method anytime that you can take your original integral problem and sort of reframe it using this format. You do need to have this kind of a nested function. So in this case, the outer function in the problem that we just worked on was the square root function. This inner function, I called it g of x, that was the 1 plus x squared. And then the derivative of that inner function with respect to x, that was the 2x dx. And since we were able to rewrite it in that format, we were able to use the substitution rule. Capital F prime equals lowercase f. What we're saying here, it's another illustration of the integration process, and that by the chain rule, if we then went and took the derivative, applying the chain rule, we would get this original expression that we were integrating again. So just seeing it in generality here, we like to do that in math. We like to show you that the format and the structure of the original problem, flowing forwards and then backwards, does indeed work. So we make those statements in generality very frequently. And here's the substitution rule written in a slightly different way, but with a comment made about the range. So if u is the inner function, g of x, right, that was the 1 plus x squared in the previous problem, if that's a differentiable function whose range, that's the output values, is a bunch of values on the interval I, and if the outer function is continuous on I, on that interval, then we are able to use this process of the substitution rule in order to do the integration. So there are some rules, some constraints that we have to abide by in order to pull the trigger and use the substitution rule. It's interesting to to think that you could actually write this. The idea of integrating dx or du, normally we don't think of these as actual expressions that you would be integrating. Really, those are thought of as, it's almost like a note that tells us what it is that we're integrating with respect to. Just like if I write f of x, this x is telling me what the independent variable is. It does also give me the opportunity to then transition and say, well, I'm going to change my x value into a 3. So there's some utility in function notation for sure. But again, this x that's in here is also telling us what the independent variable is. And there's what we were just talking about written in bold. So that is the end of the slides that are introducing us to the chain rule. Let's see another example problem. Original question is the integral of x to the third cosine x to the 4 plus 2. If we let u equal the inside function, x to the 4 plus 2, we will notice that its derivative, du, is equal to 4x to the third dx. Look back up at the original question with me. Notice the x to the third that's in here, the dx that's at the end of it, and then let your eye come back over here and notice the x to the third and the dx. But what you're not seeing is the multiple of 4 in the original question. So if I'm going to perform substitution, look back up into the top left corner. If I am going to substitute and replace x to the third and the dx, then what we need to do is come back over here to the right and solve this little equation for x to the third dx. In other words, isolate the x to the third dx on one side of that equation. If we do, it's easily done. Divide both sides by 4 or multiply both sides by 1/4. And if you do that, then that little equation changes into this one. So now on the left-hand side of this statement, I don't like that was done. The left and right-hand sides of that little equation got swapped. But now x to the third dx is on the left-hand side. Directly above it, we see the x to the third and the dx. Great, so those are what we're going to be replacing. And if we do, so if you'll bring your eye down now to here, let's continue working from there. The x to the third power and the dx are going to get replaced by 1/4 du, right? That's the substitution. Those are the two equivalent values that we're swapping out. And the other substitution performed is x to the 4th plus 2 is being replaced with the letter u. So we're seeing that double substitution again, but as I mentioned earlier, sometimes when you make this, when you take this derivative, it turns out that you have to modify it just a little bit to make sure that the factors in the original problem, in this case the x to the third and the dx, you have to isolate those on one side of your little derivative equation as you prepare to make your substitution. Okay, so now we made the substitution. I'm right in the middle of the screen, a little bit right of center. I've got this as my new integral. The constant multiple, or the factor of 1/4, can be factored outside of the integral. Excuse me, so now all I have to do is integrate cosine u with respect to u. The antiderivative of the cosine function is the sine function, so on our next slide we're seeing the sine of u. The plus c is there as our unknown constant value. The constant multiple of 1/4 is present, And then lastly, we make this back substitution in going from here to here, and we have replaced the u back with x to the fourth plus 2. Don't forget the plus c, and you've got yourself a final answer. The rhythm of this is really nice, and after you do a handful of these, I don't think that you're going to struggle with these. Maybe the biggest challenge is keeping an eye out for what it is that I'm supposed to set u equal to. And you'll know, because if you let u equal something, and then you take the derivative, and the derivative doesn't match up with some of the factors that are in your original statement, then maybe you chose the wrong expression to set u equal to. In this problem, it's pretty straightforward. The author did not show all of his work here. As you get good at these, you won't have to show so much work, but the point that's being made in this discussion is that when you're evaluating a definite integral, you've got two options. One is you can take this original statement, you can do the nothing's actually been done here except for writing the 4 and the 0 to the right of the statement. That's the evaluation that's going to happen in a moment. Then you take your integral, you do the antiderivative, take the antiderivative, find the antiderivative, figure out how to speak. Okay, I think I got it. So this is the antiderivative. There's some work that has not been shown, but if you took the derivative of this thing, you would see that you do indeed get the square root of 2x plus 1. And then, once you have your antiderivative, we have to evaluate from 0 to 4. So you plug in the 4 and you plug in the 0, and you do the subtraction between those, right? That's capital F of 4 minus capital F of 0. So you do that arithmetic, and then you clean it up, and then you get a final answer of 26 over 3. So that's one process with a tiny bit of a hand wave in there, and then there's another method. So we could do the same problem, except here using the substitution process. We're going to take the 2x plus 1 and let that equal u, which is interesting because this doesn't really look like the kind of problem you would do substitution for, because you've got the square root function, you've got the 2x plus 1 as the inner function, and after you take the derivative of that, what's that second substitution that's supposed to happen, right? Because this thing's going to turn into, it's not much of an arrow, there we go. This is going to turn into the square root of u, and then what else is left? Dx? Yeah, dx, that's all that's left. And when we let u equal to 2x plus 1 and we take the derivative of both sides, we actually initially find that the derivative of u, so the derivative of the left-hand side, becomes du. The right-hand side becomes 2 dx. And then, most of us think of the derivative of 2x. If I said, what's the derivative of 2x? Most of us would just say 2. But now that we're working with these equations where there are two variables, we need to make sure that we know what we've taken the derivative of and with respect to which variable. So having the 2x in there, or sorry, the dx in there is important. And then if we multiply both sides of this equation, if we multiply both sides of this equation by 1/2, then we get this statement right here. We have, in fact, solved for dx. So that's the other substitution that's going to happen. So let's rewrite the original problem now in terms of u. Oh, actually, we'll come back. If we write the original expression, integrand, in terms of u, doing both substitutions, you see the factor of 1/2 over here, and there's the square root of u and the du. They're all in there, all three of those components. But something else has changed. The limits of integration previously went from 0 to 4, and now they're going from 1 to 9. Why is that? The answer is because we're not working with the variable x anymore, now we're working with the variable u. 0 and 4 were x values. So we have to change those x values into u values. And how do I do that? I do that using left center of your screen. I do that using this equation right here. I take my two x values. First, my x value of 0, I plug it into that equation. 2 times 0 is 0 plus 1 is 1. So if you look over to the right-hand side of your screen, we took the x value of 0, we plugged it into that equation, and we got out a value of 1. Similarly, we take the x value of 4, so I'm back on the left-hand side of the screen. I take the x value of 4, I plug it into that same u equals equation, and we get out a u value of 9. So when x equals 4, u equals 9. When x equaled 0, u equaled 1. So that's where the 1 and the 9 come from in this integral that we're seeing. And now we can proceed with our integration. The one modification that I would make, of course, is to rewrite this as the integral from 1 to 9. I'd pull the 1/2 out front, and I would write this as u to the 1/2 power du. Increase the exponent by 1, divide by the new exponent, which would be 3/2 is the same thing as multiplying by 2/3. Don't forget to bring that multiple of 1/2 along with you, and then you get this expression right here. And now we're going to plug in the 9 and the 1 because we're integrating from 1 to 9, so we have to do capital F of 9 minus capital F of 1, and that's what's happening right down here. The multiple of 1/3 comes from simplifying the product of these two fractions. So that 1/3 is going to be present in both terms. The author here factored them out. You might just have a multiple of 1/3 inside of this term and inside of this term. That's totally fine to do it that way. You don't have to factor out the 1/3. But we're doing that f of 9 minus f of 1 process in evaluating the definite integral. And we do the arithmetic and you still get that same answer of 26/3. You might be asking the question, when do we replace u with 2x plus 1? And that's a component of this process. We didn't have to replace the u with the 2x plus 1. Instead, we changed our limits of integration. From 0 to 4, they then became from 1 to 9. So we actually modified the entire problem so that it was in terms of u, including the limits of integration, and then we were able to proceed in terms of u and get, as you can see, the same final answer. So this is only one example that it does work, but I'm telling you, it's going to work every time. At the bottom of this slide, it says, It's absurd that we observe that when using number 6, and number 6 is the substitution rule for definite integrals. Observe that when we use 6, we do not return the variable to the variable x after integrating. We simply evaluate the expression in terms of u because between the appropriate values of u. In other words, don't forget to change your limits of integration. And now just a few slides on symmetry. This is a shortcut essentially. We're going to be talking about even and odd functions. Here's a quick reminder of the definition of even and odd functions. And if you're working with an even function, then /and, if you're integrating from negative a to positive a, like from -5 to +5, so you're on both sides or sort of either side of the y-axis, then you can save yourself some trouble with dealing with that negative as your lower limit of integration, and you can simply find the area under the curve from 0 to a, and then double that area. Why does that work? Well, here we are. integrating from negative a to positive a. Our curve is symmetrical. It looks kind of like a mustache, or maybe a bird, or, okay, a bunch of things. But notice, if we integrate just to the right of the y-axis, in other words, just from 0 to a, and we get this area right here, that area is definitely the same as this area. So just find the area that's on the right-hand side and double it. And then here's a consolidated version of that statement that we saw on the previous slide. The other statement, B, that we're seeing here is that if your function is odd, and there's a reminder of the definition of an odd function, and again you're integrating from negative to positive a, then we know that the result is going to be 0. Why is that true? Because odd functions being symmetric about the origin result in graphs that look something like this. So this is just an example of a graph that has symmetry about the origin, and the area on the right-hand side of this graph, so the blue area, does have the same area as this tan-colored area in the third quadrant. The problem is, it's not really a problem, but the feature of this problem that we're highlighting is that the area that's on the left-hand side in the third quadrant actually has sort of a negative area. We don't usually call it a negative area, we just say it's still a positive area, but because it's below the x-axis, I want you to subtract it. So if you have a positive area in the first quadrant and you have to subtract the identical area that's down in the third quadrant, those two values are going to cancel each other out, and the result of your integral will be 0. This is saying what I just said, but in more formal terms. You're welcome to read that. Let's look at two examples. This one gives us a function f of x, x to the 6th plus 1. That is an even function, proven by the fact that f of negative x equals f of positive x. A negative value to an even power is going to become positive again. So it's an even function. Therefore, integrating that function from negative 2 to positive 2 is the same thing as doubling the result of integrating from simply 0 to 2. Perform the antiderivative, or find the antiderivative. There it is. Evaluate the antiderivative from 0 to positive 2. You will get the value inside these parentheses. Simplify that, and then double it, and you got yourself a final answer. This is an example of a problem from these slides. You could go into whatever textbook it is that you're using, whatever videos are provided for you by the author of your book. Go in, find a problem like this one that shows some kind of a solution process and provides you with an answer. And if it's in a video, as soon as the problem is presented, pause it, try to work it out on your own. And then if you get stumped, you can watch through to the point where maybe you got stuck. Then you can pause it again and you can continue trying to finish the solution process on your own, or just jump to the end of that portion of the video and get your answer so that you can see if your answer is what the author got or whoever is presenting in the video. So this would be a good problem to copy down onto a separate sheet of paper. I don't think I would copy this problem onto a separate sheet of paper. I'm pretty sure that I'm not going to be integrating this longhand. No. However, it is possible you do know enough math at this point to test and see if this function is even or odd. And it turns out that it's an odd function. Therefore, integrating our odd function from negative a to positive a, in this case from negative 1 to positive 1, will result in a value of 0. Don't have to do any other arithmetic but for this. That you would need to potentially demonstrate if it were in a free response question. And then you would have to state that the circumstances have been satisfied in order to return a value of 0. So it has to be an odd function, and you have to be integrating from negative a to positive a. And your integral will be 0. That's the last slide in this set of notes. Let me swap over to some homework problems, and we'll work through a few additional problems. All right. So this is a PDF version of one of my homework assignments. This is coming from WebAssign. So many thanks to McGraw-Hill for these problems. And here we're supposed to be evaluating this indefinite integral. I'll point out that I'm not going to be working any problems that require definite integrals. So I'm not going to be solving any problems where we know what the limits of integration are, right? All of these are indefinite integrals. Nor am I going to be doing any tests for symmetry. You should know how to do symmetry tests very well by this point in your studies. But let's check this one out. Notice that the derivative of this inside function, inside of my sine function, is x to the 31st, and if I took the derivative of x to the 31st, I would have an expression that has something with an x to the 30th in it. And my integrand has an x to the 30th in it. So this integral is a good candidate for the use of the substitution rule or process. So I'm going to let u equal x to the 31st. Therefore, the derivative of u will equal the derivative of the right-hand side of this equation is 31 times x to the 30th power times the derivative of x, or with respect to x. In the original problem that we're seeing here, the sine, all right, we can do it that way. Inside of the sine function x to the 31st, and only x to the 31st, is going to be replaced with the letter u, and x to the 30th, and the dx, there's the x to the 30th, and there's the dx. But this 31 is not part of my original problem, so I need to divide that over to the left-hand side of this little equation here. So let's do that real quick. I'll just put a little arrow down here that says if I multiply both sides by 1 over 31, then I get 1/31st of a du equaling x to the 30th dx. Now I'm ready to make my substitution. These factors are going to go in where those match up with. So that's the second bit of substitution that's going to happen. Too far. There we go. So now we can rewrite our original statement as the integral. Let me even rewrite this one more time. I'm going to write this as the sine of x to the 31st times x to the 30th dx, so that those two factors are right next to each other, so you can see that this x to the 30th dx is this x to the 30th dx is equal to 1 over 31 times du, so that I'm allowed to make that substitution. Of course, x to the 31st power and x to the 31st power, that's the other half of the substitution we're going to do. So we can finally rewrite this integral as the sine of u times 1 over 31 times du. The factor of 1 over 31 can be taken outside of the integral, so we could write this as 1 over 31 times the integral of the sine of u du. The antiderivative of the sine function is negative cosine. So there's the negative. There's the cosine u. And don't forget your multiple of 1 over 31 that was outside of the integral. We've integrated, so now we should put our plus c as our constant value, and our last step is to back substitute and replace u with what it is. I like to put a box around my final answer. And there it is. All the components are there. How could I possibly check my work? Is there a way to check my work? You know there is. Take the derivative of this thing and see if you get your original integrand in front of the, or to the right of the integration symbol there. You will. Don't forget that you have to use the chain rule though. If you're going to check your work on a substitution rule problem, you will need to implement the chain rule when you're taking the derivative. Let's look at another one. I'm hoping that that's going to be my u value, because that's a function that's inside of another function. The 30x plus x squared is inside of the square root function. Let's try it. Let u, terrible, equal 30x plus x squared. Therefore, the derivative of u will equal 30 plus 2x dx. Look back at the original integrand. Do you see a 30 plus 2x anywhere in here? Sort of. I see half of 1. I see half of 1. Half of 2x would be x, and half of 30 would be 15. So I'm going to go back over to the right-hand side to my du equals equation, and I'm going to multiply the entire equation by 1/2. So 1/2 du equals 15 plus x. This is still, maybe put that in parentheses, with respect to x. Now we can make our substitution. If I were using lined paper, I would say that this is on one line, and then this would have been on a second line, and on the next line, maybe I would put an equal sign over here on the left, because what I'm about to write is equal to my original statement. It's equal to the integral of the square root of u times 1/2 du. Because the 15 plus x and the dx, the 15 plus x and the dx got replaced by 1/2 du. And of course the 30x plus x squared got replaced by the u. Are we ready to do the integration yet? I'm not ready yet. I'm going to factor the 1/2 out. I'm going to rewrite the integral symbol. I'm going to change the square root of u into u to the 1/2 power. I'm not going to forget the du. Now I'm going to find the antiderivative with respect to u. The 1/2 as a factor is still there, times, I'm leaving a little space now. I'm going to have u to the 3/2 power, because I increased my exponent by 1, and then I have to divide by 3/2, or multiply by the reciprocal, which is what I'm going to do. So there's the multiplication by the reciprocal. That process, remember, is the antiderivative process. Increasing the exponent by 1 and dividing by the new exponent, or multiplying by its reciprocal. We found the antiderivative, so I'm going to include my plus c here. I'm double checking to make sure that I brought that coefficient with me. I did. The 1/2 is there. Good. I drew an arrow in here. Sorry. I drew an arrow in here. That could just as easily have been an equal sign. It would be appropriate if it was an equal sign. I am going to put an equal sign now, and I'm going to do a couple of things. I'm going to have these 2's cancel out so that I'll be left with a leading coefficient of 1/3. I'm going to replace or back substitute for u. So now I'm replacing u with 30x plus x squared. That's to the 3/2 power. Don't forget the plus c. I'm going to put a box around this as my final answer. This 3 that's in the denominator of that fraction, that you could put the entire expression. We could get rid of the 3 from here, put the whole beginning first term, and divide it by 3. That's equivalent. What else could we do? Instead of using this fractional or rational exponent, we could change we could change this and have it say 30x plus x squared now to the 3/2 power. That means that we're the denominator of that exponent, the 2, it tells me that I'm taking a square root or a second root. The numerator of that exponent, remember, tells us that we're cubing. The cubing could happen on the outside of the squaring process, or the cubing could happen, we could come inside of here, put this inner expression in parentheses, and cube that. Make sure that the cube is inside of the square root symbol, but you have to use parentheses around that inner function, the u value. So a couple of different ways that we could answer that question, or a couple of different formats for presenting our final answer. This next one is interesting. Take a look at this for a second. What do you think the u value should be? Not many options, are there? Maybe it's just the 7. Maybe it's just the 3x. Maybe it's negative 3x. Maybe it's 7 minus 3x. If it's the 7 minus 3x, if it's the whole thing, which is what it is, then usually we think of that as being the inner function. Like in the previous problem, when we set something equal to u, the u value went inside the square root function. So the u value is the inner function. If 7 minus 3x is the inner function here, then what's the outer function? If I'm replacing the denominator with a u, what was the only other element of the original integrand? It's the dx. So I better look over here in this equation and isolate the dx so that I can do that as the second part of my substitution process. When we do substitution, we do 2 substitutions. The u part, right, this has to go in there, and then some version of the du statement. I'm multiplying both sides by negative 1/3 in order to isolate the dx, and now we're ready to make our substitution. The dx in the original integrand is getting replaced by negative 1/3 du. Negative 1/3 du. I think it's a good idea if we rewrite this. How about we rewrite it as negative 1/3, since that's a constant multiple. Let's factor that out of the integral process. Now we're left with the integral of du over u. Also, maybe a little weird. You're not quite seeing where it is that we're going to go with this. Whether you keep working your way from left to right or you come down onto the next line, I don't know what you're writing on. This just helps to keep me away from those original preparatory steps that we did. I'm going to rewrite this one more time as the integral of 1 over u du. Why would I write it that way? Because the next thing I'm going to do is take an antiderivative of lowercase f, and I'm going to get capital F. Don't forget that we can check our work on our antiderivative by taking the derivative and seeing if we get the integrand again. In this case, my capital F function if I took the derivative of it, I should get 1 over u. The derivative of what function would equal 1 over u? And the answer is, it's the natural log function. The derivative of natural log of u equals 1 over u du. The du part is the chain rule part. Now all we have to do is back substitute, and we get our final answer of negative 1/3 times the natural log of 7 minus 3x plus our unknown constant. That's a great problem. That's a great expression for you to practice taking the derivative of. This is a great way for you to practice the chain rule. So we're doing the chain rule in reverse, but if you want to check your work, check and see that you got the correct final answer, do the chain rule forwards and see if the derivative of that answer is equal to, well, it should just be equal to this integrand right here. Give it a shot. Oh boy, we're into the trig functions. I'm not going to do your entire homework assignment for you. Sometimes it seems like I do. But let me make some recommendations on u values. Here I would let u equal 5 pi times t. Notice that we're integrating with respect to t. So the derivative here would be du equals, what do you think? What's the derivative of 5 pi t? Well, what's the derivative of 7x? If I asked you to take the derivative of 7x, what would you say the answer is? Hopefully you're thinking 7. And you're right, it's the constant value in front of the variable, this variable x being to the first power. It works the same way up here. If I'm taking the derivative of 5 pi t, what's 5 pi? Well, that means 5 times pi. And what's pi? It's a number. It's a horrible number, but it's a number. And what's 5? It's a number. Well, what happens when you do a number times a number, like 5 times pi? You get another number. You mean a number like 7? Absolutely. So what's the coefficient on t up here? 5 pi. So the derivative of 5 pi t is the coefficient, 5 pi. Don't forget to multiply it by dt. In the original integrand, do you see a 5 pi dt? I don't. Not outside the sine function, I don't. The only thing I see outside the sine function is a dt. So you better take this equation over here and solve it for dt so that you have the second half of your substitution prepared. And then I'm going to let you take over from there. In this problem, let's find a, this original integral is written in terms of u. That's a little tricky. We've been letting our variable be u so far. You'll have to pick another variable. You could pick v if you want to. That's pretty typical. But your v better be sharp, and your u better have a nice curve to it. Otherwise, your u's and v's could get mixed up. You could use x. That might not be ideal because normally it's an x that's getting replaced with a u, and now you're replacing a u with an x, so that could twist your mind a little bit and mess up the order of things. Maybe an r. You could use a p. What about a w? Let's use w. It's got to be a good w, though. My handwriting is usually a little too casual, but with w's and u's floating around, I better clean it up a little bit. Maybe let's let w equal, how about 1 minus e to the u? don't know, right? You're doing these problems. You don't know. How are you supposed to find out if you're doing this correctly? How are you supposed to find out if letting w equals 1 minus e to the u is correct? The answer is you got to keep going. You have to see if the thing pans out. You'll find out quickly, right? It's only going to, once you get better and better at this, it's going to take you 30 seconds to figure out if what I just wrote down is me going down the right path. What's the next thing we do? We take the derivative of both sides. So now this says dw equals, what's the derivative of a constant value? 1. 0. So we've got 0 minus, what's the derivative of e to the u? The answer is e to the u du. So 0 minus e to the u, that's kind of weird. Let's write this as dw equals negative e to the u du. And then glance back over at the original integrand. Are we seeing that over here? Well, what I see is that normally I have this statement, which is my let statement. In this case, it's a w. That substitution usually goes into an inner function. What's my inner function in this case? It's here, the 1 minus e to the u. What's it inside of? Is it inside of a squaring function? Sort of. I might take a moment and see if it's worth my while to rewrite the original problem as e to the u times, instead of divided by, 1 minus e to the u. I just can't turn that into a u. Come on. It's just bad. I'm just bad. To the negative second power. Now that 1 minus e to the u is looking like an inner function, and the outer function is the power of negative 2. Okay, so if that's true, I'm stuck with that. Can I get it? Can I get it? Got it. All right, let's make a substitution now. Let's make both substitutions. We know that there are always two. W is going in for this 1 minus e to the u. And now I need an e to the u du. Where do I look for it? Over here. It's pretty close. Here is the e to the u du, but I don't want it to have that negative sign in front of it. So let's multiply or divide both sides by negative 1. That takes this equation and makes it negative dw, that's not a w, there we go, equals positive e to the u du. That's looking good. Now we're ready to make the substitution. We've got the e to the u du isolated, and coming back over toward the left, I can rewrite this as the integral of w to the negative second power times negative dw. That negative sign, we're going to factor it outside of the integration process. Make sure that that negative that you've written down outside of the integral is strong enough that you can see it, so you don't end up leaving it behind. Now you have to find the antiderivative of w to the negative second power. Back substitute, and don't forget that negative sign that was outside the integral. So I'm going to let you take care of the rest of that. Tricky. Oh, we're pushing the 1 hour mark, so in number 6, I'll ask you, what's the inner function? We like to use the substitution rule or the substitution process when we have the integral of f of g of x times g prime of x. This format has to match this format. So I ask you to find the inner function, g of x, what's the outer function? F. That doesn't matter so much, except that it's going to be the outer function is going to be encapsulating the inner function, the g of x. It's the g of x function that gets replaced with the u. And then somehow this ends up being du, and it's got a dx in there, and so you have to prepare to make that second round of substitution. But figuring out what your inner function is very important, and the derivative of that inner function better also be present in your integrand. This one also tricky. Figuring out the inner function, the derivative of something in this integrand should equal something pretty close to the rest of the stuff that's in this integrand. Maybe tangent is your u value. Maybe secant is your u value. In that case, you would have u squared. Or if tangent is equal to u, then it's u to the third power. And then the derivative of one of those maybe equals the other one of those. So you'll have to tinker with that. And we know that the derivative of e to the x is e to the x. So your inner function, I think, is pretty obvious on this one. And I would not hesitate to change this into sine to the negative 18th power and put it up into the numerator. Something pretty similar on that one. You've got a double angle identity maybe. I haven't looked at that one at length, but just in case going over the 1 hour mark messes me up, I'm going to dip right now. I wish you the best of luck with the rest of these problems. I hope this was helpful, and I look forward to seeing you again. Take care.